Alright, so last time we started looking at the general exponential function a to the x, and there are a couple of things that we said here. When we looked at the first derivative of a to the x, we saw that the first derivative is positive for any x when a is greater than 1, and the first derivative is negative when a is between 0 and 1, for any x. Notice that I did not include a equals to 1. Remember, I spoke about the case a equals to 1. When a is equal to 1, the function is what? When a is equal to 1, what's the function? When if you have a is 1, right? If you have a is 1, that means I have 1 to the power what? 1 to the power x. By definition, this is what? E to the x ln of 1, which is e to the x times 0, which is e to the 0, which is 1. So this is for any x, right? This is for any x. So that means when a is 1, this is a fake exponential function. That is, this function is actually the constant function one, right? Why do I say it's a fake? Because it's when we talk about exponential function, we don't mean that one, right? Is everybody clear? Alright, so and then we also looked at the second derivative, and we decided that the second derivative is always positive, therefore the function is concave up on the entire real line. So then using these facts, let's see if we can come up with the graph of the a to the x function. But the graph will depend on, there are two cases to look at: when a is larger than 1, when a is less than 1 but greater than 0. So let's look at those cases. One thing I want to mention here, this is just a remark. Suppose that I am looking at the function b to the x, and let's say the number b is between 0 and 1. The number b is between 0 and 1. Then I can express b as 1 over a, where a is larger than 1. You agree? If I have a number between 0 and 1, I can always express it as 1 over a, where a is larger than 1. You might say, well, given b, what is a? Well, notice that I could say a is what? A is basically 1 over b, right? So if I take a to be 1 over b, then b is 1 over a. Am I making sense? Of course, 1 over b would be larger than 1, right? Because b is between 0 and 1. So if you divide 1 by something between 0 and 1, wouldn't you get something bigger than 1? Like divide 1 by 0.5 or 0.1 even, you get something bigger than 1, right? So my point is, if I have a number, if I have the function b to the x, where b is between 0 and 1, I can think of that as 1. I can think of b as 1 over a. So that means, what is b to the x? B to the x is 1 over a to the x. Is everybody okay with that? You guys are okay with that? Now, remember, we have this power rules here. Those power rules imply, those power rules that we stated, they imply that this is the same as 1 over 1 to the x over a to the x and that implies that I have 1 over a to the x, right? You guys agree with that? This is the same as a to the 0 over a to the x, and I can think of this as a to the 0 minus x, which is negative x. All I'm saying is there are different ways of thinking about the case where the base is less than 1. When the base is less than 1, I can think of that as the same as 1 over a to the x for some a, or I can think of it as a to the negative x, where a is bigger than 1. Is that okay? So what are we saying then? We are saying that the function b to the x is the same as a to the negative x is the same as 1 over a to the x, right? This is the case where b is between 0 and 1 and a is 1 over b. So I can express the function b to the x in this way. You guys get my point? Okay, so then basically what I'm trying to do here is convince you that if I have to sketch the graph of b to the x, where b is between 0 and 1, I am basically graphing, coming up with the graph of a to the negative x, right, where a is a number bigger than 1. What's the graph of b to the x is the same as graph of a to the negative x. What's the relationship between a and b? Well, a is 1 over b. Right? A is 1 over b. So a is bigger than 1, b is less than 1. Okay. Let me then go ahead and draw the graphs. In this case here, so first of all, I'm going to draw the case where a is the base is bigger than 1. What is a to the 0? Oh, sorry. I need it a little bit right here. What is a to the 0? I'm trying to draw the graph of a to the 0. So this is y equals to a to the x. This is the x-axis, and I am assuming here this is the case where I am taking a to be larger than 1. I know what is a to the 0? 1. So let's say 1 is right here, and I know that the graph, when a is greater than 1, the graph is concave up and what? Increasing everywhere. So then the graph is concave up, increasing everywhere. Do I know how? Well, I forgot to address two more things. One is, in this case, what's the limit as x goes to infinity of a to the x, and what's the limit as x goes to negative infinity of a to the x? What are these limits? What's that? Go ahead. Yeah, it's exactly the same as what happens for e. That is, this is the same as, remember, the limit as x goes to infinity of e to the x ln of a. Now, as x goes to infinity, the exponent goes to infinity because ln of a is positive. So if the exponent goes to infinity, e to the that will go to infinity. And the second case, you have the limit as x goes to infinity, negative infinity, e to the x ln of a. And right now ln of a is still positive, but x is going to negative infinity, so the entire exponent is going to negative infinity. So e to the that will go to 0. This is from the facts that we know from the exponential function e to the x. So what's the graph then? Well, the graph will be, it is going to 0 here, and then it is going to it is going to infinity. Okay, so that's how the graph should look like. Is everybody okay with that? So that's the case when a is greater than 1. Can someone tell me what would be the graph of a to the negative x? Still a is greater than 1. If a is greater than 1, what's the graph of a to the negative x? Do I need to worry about concavity and so on? No, I can think of the graph of a to the, there is a relationship between the graph of a to the x and the graph of a to the negative x. What is that? What's the relationship between the graph of a to the x, graph of a to the negative x? Yeah. What's the relationship between the graph of f of x and f of negative x? It's a reflection across the y-axis. So the graph of a to the negative x, the graph of a to the negative x will be something like this. Okay, so the black one here so the black one here is the graph of a to the negative x, which is the same as 1 over a to the x. Okay. So you might ask, hey, what's the graph of a to the x when a is between 0 and 1? When a is between 0 and 1, the graph of a to the x will look like the black curve, right? Because what is 1 over a? 1 over a is between 0 and 1, right? In our picture, a is bigger than 1. If a is bigger than 1, 1 over a is smaller than 1, right? So when the base is between 0 and 1, the graph is concave up but decreasing, right? You remember that? So exactly the black curve. Am I making sense? So that's how the graph looks like. But let me still make another graph just to complete my discussion here. So let me make one more curve here, and this time let me use green. This is a to the 0. This is the case where I'm taking y to be a to the x, but here I am taking a between 0 and 1, when then the graph I know is still concave up but decreasing. How do we know that? Because we know the derivatives, right? Okay, so that's the graph of a to the x when a is between 0 and 1. Any questions, anybody? If you look at my first picture, if I ask you what's the graph of 2 to the x, what did you say? What's the graph of 2 to the x? It looks like the blue one or the black one? Blue one. And what's the graph of 2 to the negative x? The black one. If I say, instead of saying 2 to the negative x, if I say half to the x, what's the graph of half to the x? It's still the black one, right? Everybody sees those? Okay. Okay, so now you know the graphs, and you need to remember this type of these graphs, and in order to answer limit questions, right? So if someone asks you if someone says what's the limit as x goes to negative infinity of half to the x, what did you say? Well, you can if you remember the graph of half to the x, right, you know that it is going to infinity at negative infinity, right? The graph of half to the x will look like this green curve, right? Because this is the case when a is between 0 and 1. However, I could also say that this is equal to the limit as x goes to negative infinity of 2 to the negative x, and this is the limit as x goes to negative infinity e to the negative x ln of 2. ln of 2 is positive, so if x goes to negative infinity, the exponent is going to positive infinity. E to the something going to positive infinity is positive infinity. I can answer it by switching the problem in terms of the e to the x function and then answer it. Or I can directly know the behavior of half to the x, right? We just drew the graph of a to the x when a is between 0 and 1. If I remember that, I know exactly what should be the limit. Is that making sense? All right. Let me ask you a couple of questions here. Look at the pictures here. If I ask you, what's the limit as x goes to infinity of a to the x when a is between 0 and 1, what did you say? What's the limit of a to the x as x goes to infinity in the case a is less than 1? Zero, because that's the second picture. And if I say what's the limit of a to the x what's the limit of a to the x as x goes to negative infinity when x is when a is bigger than 1? A bigger than 1, limit of a to the x goes to negative infinity. 0 again, right? That's the blue curve, right? That's the blue curve. A to the x goes to negative infinity, a is greater than 1, that's the blue curve. So it goes to 0. Again, you have to be able to understand those questions. And I'm going to be assigning some web assigned homeworks so that you have some practice on how to answer these questions. So now what I want to do is some more exercises on finding derivatives. Remember I talked about the function x to the root x, right? So the question is, what's the derivative? What's the derivative of x to the root x? Okay. How would you find the derivative of x to the root x? So this is equal to, I have to appeal to the definition of x to the root x. What's the meaning of x to the root x? Do not say that the derivative of x to the root x is by power rule root x to the root x minus 1. Let me write it in red, okay? Because I see that a lot of the times a lot of people will say the derivative is root x to the root x minus 1. Why? It's the power rule. But the power rule only applies when the exponent is constant. Power rule only applies when the exponent is constant. Okay? This is completely wrong, okay? So what's the right way of doing it? Well, remember what's the definition of that? This means e to the power exponent times ln of the base. You appeal to that definition and then you take the derivative. What's the derivative of e to the power something? You did this in your exam. E to the, so it is itself multiplied by the derivative of the exponent. What's the derivative of the exponent? I have to use the product rule. It'll be root x times the derivative of ln of x, which is 1 over x, plus it's the derivative of root x, which is 1 over 2 root x times ln of x. So that's the derivative of the exponent by product rule. What is e to the root x ln of x? Well, it is still x to the root x, right? And within the brackets I have 1 over root x plus ln x divided by 2 root x. And finally, if you want, you can simplify a little bit by factoring out 1 over 2 root x. Okay, you can factor out 1 over 2 root x if you want to, and you still have x to the root x. Oops. Okay. All right. So I was going to write 1 over 2 root x times x to the root x multiplied by what would I get within the parentheses? What am I going to get within the parentheses? I'm going to get a 2 plus ln of x, right? We factored out 1 over root x and also a half, right? So because of I factored out half, I'm going to get a 2. And from the second term, obviously ln of x is remaining. Is everybody okay with that? Is that algebra okay with you? All right, so that's the derivative of x to the root x. I want to do this problem a little bit differently, because sometimes people prefer the other way. So this is one way of doing this problem, but there is another way as well, which is a log differentiation. So I'm going to redo this problem. So redo. How am I going to redo this? Well, let's say I have y equals to x to the root x, right? And what do I want to find? I want to find y prime. So before what I'm going to do is use log differentiation. Remember the idea of the log differentiation. You take ln of both sides. So you take ln of x to the root x. Now, what is ln of x to the root x? It is root x ln of x. Why? Because the exponent here can be moved in front of the log function by one of the properties of the log function. And then I take the derivative of both sides with respect to x. So I take the derivative with respect to x of ln of y. I take the derivative with respect to x of root x ln of x. What's the derivative on the right hand side? By the product rule, I get root x, right, 1 over x, plus the derivative of root x is 1 over 2 root x, and ln of x, right? That's the product rule. What's the derivative on the left hand side? The derivative on the left hand side is 1 over y times y prime. And I have to solve for y prime. So what is y prime? Y prime would be y, and within brackets I have 1 over root x plus ln x over 2 root x so I get y prime. Remember what y is? Y is x to the root x, so I have to plug that in again, and then I still have that 1 over root x plus ln of x over 2 root x, and then you can do the simplification that I did as before, right? So this is another way of doing it, using the log differentiation. The amount of work that is needed in both ways is the same, exactly the same. Okay, it's up to you which one you like more, but you should know both ways, because people use both ways in different texts and so on. So if you read something, a book in future, you need to know both ways. Any questions on that? Yeah.
How does the square root of x times 1 over x equal to 1 over
Because root of x and x cancels out to, I mean, what is root x? So what is, let me use red. What is root x times 1 over x? This is what you're asking.
Yeah.
And then root x is actually half divided by x, right? That's what I have. But what is actually half over x? This is 1 over actually half, right? You're going to subtract the exponents, right? 1 minus a half, that will be actually half. But what is 1 over actually half? That's 1 over root x. Is that? So that's yeah. So that's the explanation there. Any questions, anybody? It's like writing root 2 times 1 over 2, right? If you write root 2 times 1 over 2, that's root 2 over 2, which is the same as 1 over root 2, right? So root 2 over 2 is the same as 1 over root 2. All right. Let's move on to another problem. Let's say I have the function y equals to 5 to the negative 1 over x. What's the derivative? Well, there would be two ways of going about it, okay? One is I can remember the derivative formulas for a to the x. What's the derivative of a to the x? The derivative of a to the x is a to the x itself multiplied by ln of the base, ln of a. So what's the derivative of 5 to the x? The derivative of 5 to the x would be 5 to the x ln of 5, right? But I have 5 to the negative 1 over x, so I have to apply the chain rule here. So again, let me remind you that the derivative of 5 to the x by my formula would be 5 to the x itself times ln of 5. Very good. So then what's the derivative of the function that I have? The function that I have, this is the composition of two functions, 5 to the x and negative 1 over x. Right? And so I have to apply the chain rule. So basically what it comes out to, I wish the exponent was just x. If the exponent were just x, then the derivative would be 5 to the x, assuming that the exponent is just x. But it isn't x, okay? So I have to multiply by its derivative. What's the derivative of negative? What's the derivative of negative 1 over x? Oh. Nobody said, no one said anything. Okay? What did I do wrong? If the exponent were just x, then the derivative would be 5 to the x times ln of 5. I forgot about ln of 5, right? Then multiply by the derivative of the exponent. What's the derivative of the exponent? What is the derivative of the exponent? The exponent is negative 1 over x, right? Let me write d dx of negative 1 over x. So what's the derivative of that? Very good. This would be negative. Okay, so this is what? This guy here is basically negative x to the negative 1. So when you use the power rule, you're getting x to the negative 2. And x to the negative 2 is exactly 1 over x squared. Okay, so that's the derivative. So what did I do here? Well, I had to remember, first of all, the derivative formula for a to the x. And I had to use chain rule. Is that clear? Now, I'm going to redo this problem in a bit differently, okay? Is everybody with me? Okay, so let's, are you guys done writing it down? So let me show you yet another way of doing this. Okay, so redo. Why am I showing you all this? Not to confuse you, I just want you to pick up whichever you like, okay? I want to show you all the different ways that I know of writing this solution. So what is, let's say I have y is 5 to the negative 1 over x. Now before I take the derivative, I am just going to apply the definition, which is this guy, I can express it in terms of the e to the x function. It is e to the what? Somebody please say, what is the exponent? E to the power what? What goes in the exponent? When you convert an exponential in terms of e, what goes in the exponent? What's that? Yeah, it's the same exponent multiplied by ln of the base. That's what you get. Right? Now, I take the derivative now. What's the derivative? What's the derivative of e to the power something? It is exactly itself. It is exactly itself multiplied by the derivative of the exponent. What's the derivative of the exponent? ln of 5 is fixed, right? ln of 5 is fixed. So this would be ln of 5 multiplied with the derivative of negative 1 over x. You agree? I am taking the derivative of the exponent. The exponent is negative 1 over x ln of 5. ln of 5 is a constant factor, so I'm going to get ln of 5 times the derivative of negative 1 over x. What's the derivative of negative 1 over x? 1 over x squared. We saw that before. Well, is it the same as what I had before? Well, this quantity here is still what? 5 to the negative 1 over x, right? This quantity is still that ln of 5 1 over x squared. What's the advantage of this method? Well, I didn't have to remember the formula for the derivative of a to the x. Okay? All I had to remember is what I have to know already, which is how to find derivatives of functions like e to the power something. And you should know this by now because your exam had a question like this, right? Alright, this is that. Do you want me to do yet another way of doing this problem? Well, what the heck, let's do another way, okay? So redo once again. I have y is 5 to the negative 1 over x. And this is the log differentiation way. Okay, you take ln of y, you take ln of 5 to the negative 1 over x. This is ln of y, negative 1 over x, ln of 5, right? This is one of the properties of log. The exponent that I have here, that can be moved in front of the log, and then I take the derivative on the left. I get 1 over y prime, and I take the derivative on the right. Ln of 5 is a constant factor, so that's going to remain. So ln of 5 multiplied with the derivative of negative 1 over x. The derivative of negative 1 over x is 1 over x squared, right? You don't have to do it in your head. You can just write it out if you want to. And then I solve for y prime. Y prime is y times ln of 5 times 1 over x squared. But what is y? Y is 5 to the negative 1 over x. Ln of 5, 1 over x squared. Okay, I gave you 3 ways, and I don't know if there are any other ways, okay? I doubt there are any other ways of doing this, but you can pick whichever writing style you like better. For me, these are just a matter of style rather than really, they involve about the same amount of work, right? If you look into them, you will see the number of steps, or you didn't reduce the number of steps or anything else. It's just a different ways of writing the same solution. Whichever you like, use it, and you'll be fine. Any questions on what I did? Okay. 10 minutes. Okay, 10 minutes. Since I have 10 minutes left, let me stop doing exercises on derivatives. I'm going to do more exercises on derivatives later, maybe tomorrow. But what I want to do is, okay, we talked about the general exponential functions, right? How about the general log functions, right? So now the general logarithm, I'm just going to say logarithm function. Okay. And okay, so how do we define the general? So remember, our quest was we defined ln, then we defined e to the exp function in terms of, let me actually write it down. So remember, we defined ln of x essentially in terms of areas below the graph of 1 over t, right? We defined ln of x. Here x is larger than 0. We define ln of x in terms of areas below the graph of 1 over t. That's what the integral represents. And then we define the function exp of x. What is the function exp of x? The function exp of x, the exponential function, was the inverse of ln of x, right? This was the inverse. This was the inverse of ln of x, right? And we came up with the graph and so on for the exp of x. And then what I did was I said, then I defined for you then I gave you a definition of e to the r for rational r. So I told you what is the meaning of e to the n when n is a positive integer. What's the meaning of e to the negative n? What's the meaning of e to the m divided by n? Right? I gave you a meaning of e to the a rational exponent. I defined it for you. Right? What's the meaning of that? What does it mean to raise e to a rational exponent? I told you that. Independent. I didn't associate that with exp. And then I said, then we showed that e to the r is equal to exp of r for rational number r. You guys understand what I'm saying? exp was defined, e to the r was separately defined independently, and then we showed e to the r and exp of r, they agree for any rational r. But then we asked, hey, what does it mean to raise e to a irrational exponent? We didn't have a meaning of that. Okay? And then I said, well, if I have, because e to the r and exp of r, they agree for rational r, well, why don't we, if I have an irrational number like root 2, I'm just going to define it to be the value of the exponential function at root 2. Okay? It makes sense to make that definition because e to the r and exp of r are the same for any rational r. So for irrational exponent, I'm just going to make that definition. And after that, once I make that definition, then e to the x is basically exp of x. The meaning of e to the x is the same as exp of x. Right now, they are synonymous for us. Okay? Raising e to x is the same as evaluating exp at x. exp is the inverse of log. Well, very good. So then what did we do? Well, we then defined a to the x to be e to the power x ln of a, and this we did for positive a. Then we said, what does it mean to raise a to x, right? And we said, well, it means that e to the x ln of a, right? And more generally, we said, well, what is x to the power root x? Well, that would be the same as e to the power root x ln of x. So generally speaking, what I said is, if I have a base function, if I have a exponent function, then the meaning of that is e to the power g of x times ln of the base. Of course, like here, I have to have the base is positive. Here, I also want the base to be positive. Okay? Those were the definitions we made after that. So those are the general exponential functions. Now we want to talk about the general log function. And how would I define that? Right? How would I define that? First of all, I defined exponential as the inverse of the ln function, the natural log. I'm now going to do the opposite. I have a definition for a to the x, and I'm going to define the log base a as the inverse of a to the x. Remember, a to the x is either increasing or decreasing, so a to the x is always 1 to 1. So it has an inverse. Okay? So note a to the x is 1 to 1. Okay, a to the x is 1 to 1. So it has an inverse. Okay? And what would be our notation for the inverse? So here I'm going to let a to be greater than 0 again. And this time I'm also going to say a is not 1. Remember, when a is 1, the exponential function is what? When a is 1, a to the x is just the constant function 1. And the constant function 1, is that 1 to 1? The constant function 1, is that 1 to 1? That's the worst function to be 1 to 1, right? Because it's always 1, right? It couldn't be 1 at all. So that's why I am getting rid of that. But if I get rid of the case a equals to 1, then a to the x is always 1 to 1. Why am I getting rid of the case a equals to 1? Because when a is 1, a to the x is not 1 to 1, right? Okay, so now what's the inverse? I'm going to denote the inverse by the following. LOGA, base a of x. And that's the notation for the inverse of a to the x, period. Okay? Now, let's think about the domain of a to the x. What's the domain? What's the domain of a to the x? What's the range? What's the range of a to the x? Someone please say, what's the domain of a to the x? We looked at the graph, so you better know what's the domain, right? The domain of a to the x is, all real numbers. We defined it for all real numbers. And what's the range? Remember, a to the x is always positive, 0 to infinity. So what would be the range of log? The range of the log base a, would be the domain of a to the x, and the domain of log base x a would be the same as the range of a to the x. Notice it is exactly the same. Domain and range are exactly the same as ln and e to the x, right? Nothing changed. If you know the domain and range for e to the x and ln of x, you know the domain and range for any log base a. Right? Exactly the same. Okay? Alright, so what is the meaning of inverse? Once again, it means that if I am looking at log base a of x, log base a of x is equal to y, if and only if what? If and only if a to the y is equal to x. Right? What is it telling me? It's telling me that if I have a number x and if I have another number y, if the log base a, if the log base a is taking x to y, then the function a to the something, right, a to the y, the exponential function then is taking y back to x, right? That's the property of inverses. They do the opposite of each other. Okay, they undo each other. And what's the cancellation properties? Remember, whenever you have a pair of inverses, there are two cancellation properties. What are they? The cancellation properties are, if you take the composition of the two functions, you're going to get the identity function, right? So what is a log? What is log base a of a to the x? That is x for x between negative infinity to infinity, because x is in the domain of the exponential. And then if I take a to the power log base a of x, it is also x. In this case, x is in the domain of the log function. These are the cancellation properties for the general log and the general exponential function a to the x. You guys are okay with that? Okay, I'm going to end here. We are out of time, and I have to still finish more stuff. Okay. You can start doing the homework on 7.4 star, but there are certain things that we still have to finish.